Hello guys, welcome. In this video, we will learn about whole numbers, integers, remainder theorem and divisibility rules. So let's get started. So in the last video, we saw what are natural numbers. So natural numbers are counting numbers. So they start from 1 and they go on 1, 2, 3, 4 and so on. So today we'll see about whole numbers. Whole numbers are natural numbers plus 0. So it includes all the numbers 0, 1, 2, 3 and so on. These are whole numbers. So 0 has a special property. So whenever we add any number to 0, it gives the same number. So any natural number or whole number added to 0 will give the same number. And also if you multiply any number with 0, it gives 0 itself. Since we introduce only natural numbers and whole numbers so far, I am saying like this is true for any natural number n, but in general it is true for any real number or complex number n. So we'll not get into it now. We'll see them as we go on. So the next is integers. So we had 0, 1, 2, 3 and so on. But there was also a need for negative numbers. Let's say if you want to represent profit and loss. So for easy calculation, there was a requirement that profit be represented by positive numbers and loss be represented by negative numbers. So they also introduced -1, -2 and so on in the other side, in the negative direction. So this entire set of numbers are called as integers. So when you add a positive number, let's say +1, to its counterpart negative number, we also get 0. So any number plus its negative counterpart will give us 0. Okay, so this with whole numbers and integers, we can now go into what is called as the remainder theorem. So we already know what a remainder is, right? So when we take a number, let's say d, and divide it by some other number, then we get some quotient and some remainder, so that we can represent this number d as q into d plus r. So remainder is the residue when one number is divided by another number, right? So for example, let's say 30 is divided by 7. We have the division methodology, right? 30 and 7. So 4 times we get 28 and 2. So 4 is the quotient and 2 is the remainder. So 30 can be represented as 4 into 7 plus 2. So this is same as this one, right? So this is the general one. Suppose we have more numbers. Let's say I want 1 plus 27 plus 51 plus 67. Okay, so I want to find the remainder when this result is divided by 6. Let's say 6. So in general what I will do, I will go and sit and add these numbers. So 1, 27, 51, 67. I'll add it. 14, 16. So 3, 8 and 14, 146. Then I will go and divide. So this is 6. Okay, so it is 2 times 12. Then we have 26, which will be 4 times 24. So the remainder is 2. So this is the straightforward method. But there is a shortcut. So we will see what that is. I will just illustrate it now. I'll give the proof after that. So I'm going to divide each of this number by 6 and take the remainder. Okay. So 1 when divided by 6 gives 1 as remainder. So 27, I know 24 is divisible, so the remainder will be 3. 51 again, 48 is 6 into 8, so the remainder is 3. And 67, 66 is 6 into 11, so this is again 1. Now I am going to add this plus sign, I am going to bring it as it is. So what I get? 1 plus 3 plus 3 plus 1, which is 6 plus 2, which is 8. Again I divide this by 6. What remainder I get? I get 2. So this is the 2 we got. But even when I took the individual numbers and then I found the reminders of them and added them, because the numbers itself are added, and then the final result, when I again divide, the final result also is giving the same reminder as the original number. So why this is the case? This I illustrated for one example, but this is the case for all numbers. Any number you take and divide, this method will work. So let's see why this is working. So now let's say we have the numbers n1, n2, n3, n4. Let's take for 4 numbers for this example, and we can also extend it to any number of numbers. Now let's say we want to find this remainder when it is divided by some number d. Okay, let this number be x. So now x is nothing but, the remainder will be nothing but some quotient into d plus that r, right? We need to find the r. Now what I am saying is, I'll take each of these numbers and divide. So each of these numbers will also be some multiple of d plus r1, right? There will leave some remainder. So n2 again we'll have q2d plus r2. Similarly for n3 we'll have q3d into r3, and n4 we have q4d into r4. Now we add all these. So left hand side we have n1 plus n2 plus n3 plus n4 is equal to q1d plus q2d plus q3d plus q4d. So d is common in all this. Let's take it outside. Plus r1 plus r2 plus r3 plus r4. Now you can compare these two expressions, right? So whatever is the remainder of x, it will also be the remainder if we divide this number by this number d, right? Because this is divisible by d, so this will never come into the remainders picture. So this we can neglect. So now we have r1 plus r2 plus r3 plus r4. Now if we again, this number we can repeat the same thing, and finally if we end up with a number less than this d, then we can say it is the remainder r. So that is why it is working. This is because these quotients never come into picture, and it is only at the final, it is only like adding these reminders of these individual numbers. Okay, so now if we have another number n1 into n2 into n3 into n4, now it is multiplication. In this case, is it still applicable? So again, so n1 we can write it as q1d plus r1, q2d plus r2, q3d plus r3, q4d plus r4. So now we will group all numbers which is divisible by d and which is not divisible by d. So you can see this q1d, with whatever number it is multiplied, it will be divisible by d, right? So this will fall under divisibility of d. Now if you take r1 into this number, let's say, again this has d, so this will be multiple, this will be a factor of d. So again this will not come into the remainders part. So r1 into r2 let's take. Now still we don't know if it is divisible by d, so we consider r1 into r2. Now again we take this and go to q3 into d. Again d is there, so this term will again be present here. So we have r3 here, So we'll have R1, R2, R3. Now again, this, when we multiply with this, D is present, so this will include here. And then we have R1, R2, R3 and R4. So finally what we'll get a bunch of terms which is divisible by D plus R1, R2, R3, R4. So initially we started with, we want to find the remainder of N1, N2, N3 and N4. But finally we ended up with the product of the reminders. So this is applicable even for the reminders. So I'll just summarize whatever I have said. So to find the remainder of A plus B plus C plus D and so on, it is sufficient to find the remainder of the sum of remainders of A plus B plus C plus, sum of remainders of A comma B comma C comma D and so on. Similarly, this is the same case for A into B into C into D and so on. It is just necessary to find the product of reminders, remainder of the product of reminders of A comma B comma C comma D. So I already gave an example for the first case. I'll give an example for the second case also. So let's say we want to find 1 into 2 into 3 into 4 when divided by 7. So what is this? I'm taking a simple example. So it is just 6 into 24, which is 24. So 24 divided by 7. 3 times it is 21. We have 3. So the remainder is 2. So, okay, this is the simple case because, 1 into, again, this one you can't simplify because it is already, the reminders are of each individual are same as the numbers. So what I'll do, I'll multiply this way. No, or I will multiply 1 into 2 into 12. So 12 when divided by 7, the remainder will be 5. So 2 into 10 into 1. So 1 into 10. So 7 again, the remainder will be 3. So now the final answer will be 3. This is same as the one here. So we needn't multiply all the numbers and then take the remainder. Instead what I did is I grouped two numbers and then I found a new number, and then from that I took the remainder of that number and again I found multiplied with another number and then I found the remainder of that. So this way it becomes simpler for bigger numbers, and also if there are more numbers in the multiplication, this becomes simpler. So this is all with the remainders theorem. Next we will see the divisibility rules. So divisibility rules will help us find if a given number is either divisible by either, let's say, 2 or 3 or 4. So if I give just a big number 1, 2, 5, 6, and if I ask if it is divisible by 3, so again there are certain rules which we can say it quickly whether it is divisible or not. So we will see that one by one for let's say first 50 natural numbers. So the first one, 1 we know it divides any number. So any number is divisible by 1. We know, don't even need any rule for that. 2. So 2 is also easy. Why? Because any even number, right, is divisible by 2. Okay, then you might ask how you will find if a number is odd or even. So units digits, right? If it is 2, 4, 6, 8 and 0. If it ends with these numbers, then it is an even number. Okay, why is that the case? Any number, right? Any number if you take, let the unit digit be y and the tens digit and the remaining digits be x. So for example, I'll take 246. This can be written as 24 into 10 plus 6. So this is nothing but x and y. So it's 10 into x plus y. That is what I'm saying. So any number can be written like this, and y will always belong to from 0 to 9. And x can belong anything. It can be also greater than 9. It can be 10, 11, anything. In this case it is 24, right? Okay. So now if you see this 10x, 10 is nothing but 2 into 5 into x plus y. So this itself is divisible by 2. So using the remainders theorem, in the remainder this will not come. So only y will come. That is why we say either 2, 4, 6, 8, 0. We know that 2 is divisible by 2, 4 is divisible by 2, 6, 8 and 0 are divisible by 2. That is why it is just sufficient for us to find y is divisible by 2. Y is nothing but the units digits, units place. Okay, so let's take an example. This is using remainders theorem. Let's say 26. You can see in the units place it is 6, which is a even number, so it is divisible by 2. So I think number 2 is fairly simple. Everyone will be knowing it. Now let's jump to number 3. So number 3, there is a special property. They say, let's say the number is like x, y, z, or let's say a, b, c, d, 4 digit, or it can have any number of digits. If you add the sum of digits, if the sum of the digits is divisible by 3, then the number is divisible by 3. I'll give you an example. 123. So looking at the number, we couldn't find if it is divisible by 3. We have to go and divide. But if you just add these digits, right, it gives 6. 6 very well we know it's divisible by 3. So they are saying the number also should be divisible by 3. So we'll see the proof for this. So again, so I'll take for example a 3-digit number xyz. It can be represented as 100x plus 10y plus z, correct? So 123 is nothing but 100 into 1 plus 2, 10 into 2 plus 3. So that is what I have written here. Now this, we want to check the remainder when this is divisible by 3. And if the remainder is equal to 0, then we say it is divisible by 3. If the remainder is not equal to 0, we say it is not divisible by 3. So again, we'll deal this separately. So 100 into x. This divisible by 3 is nothing but, 100 we can reduce it further. So 100 will be nothing but, what will be the remainder when 100 is divided by 3? So 33 into 3 will be 99. So 100 is nothing but remainder is 1. 1 into x, which is x itself. So this we can convert as x plus 10y. 10 into y. But 10 is nothing but 3 into 3 plus 1. So by remainder theorem, this is same as 1 into y. So y plus z. So from the original number, we have now come to the sum of the digits. So this is same for even the higher orders. If you take 1000 also, 1000 is nothing but 333 into 3 will be 999. This will again give the remainder of 1 when divided by 3. So that is the catch. 10 power any x, any natural number, when divided by 3 will give a remainder of 1. So that is why from any number we can convert it to the sum of digits. It is just sufficient to check if the sum of the digits are divisible by 3. Okay. Now let's jump to 4. Number 4. So number 4. For number 2 we said just the unit digits is sufficient. Because we said the 10x plus y. 10 was divisible by 2. But if you see 10 is not divisible by 4. Right? It is not divisible by 4. Okay. Let's check for 100. Is 100 divisible by 4? Yes. 25 into 4 is 100. So 100 is divisible by 4, right? So we can write any number as, let's say 100a plus b, where b is 2 digits, last 2 digits. Correct? For example, 252. This I can write as 100 into 2 plus 52. Now we know this number is divisible by 4. So it is just sufficient for me to check if b is divisible by 4. Just the last 2 digits, if I check if it is divisible by 4, it is sufficient. In this case 52. 52 is nothing but 13 into 4. So hence it is divisible by 4. So this number 252 itself is divisible by 4. So for 4, last 2 digits, check last 2 digits if divisible by 4. It is good enough. Okay. Next is number 5. So for 5, if you see, I'm writing the multiples of 5. So 5, 10, 15, 20, 25, 30, 35, 40 and so on. So what do you observe? Like the last digits is either 0 or 5. Correct? So again for 5 also it is easier. Just the last digit you have to check if it is divisible by 5. Again, why is this the case? Similar to the number 2 we checked, right? Any number is represented this way. This one is divisible by 5. So this never comes into picture. Only the last digit we are concerned. For it to be divisible by 5, it should be either 5 or 0. Okay. So this is for number 5. Fairly straightforward. Next we'll go to number 6. So number 6, what should it be? 6 is nothing but 2 into 3. So if any number, notice that 2 and 3 are prime. So any number, if it is divisible by 2 and it is divisible by 3, then it is also divisible by 6. So it is not or, it is and. So which means the number should be divisible by 2 and 3. For example, let's take 24. So it is divisible by 2 because the last digit is 2. Divisible by 2 is correct. And 2 plus 4 is 6, which is divisible by 3. So divisible by 3 also is correct. Hence it is divisible by 6. So this is the condition divisibility rule for number 6. Next for number 7, let's see. 7 is little involved. So for this I'll first state the divisibility rule, then I'll give you the proof. So for this number they say, I'll illustrate with an example. Let's take okay 147. For this they say, take the last digit, okay, 7, multiply it by 2, 14, and subtract it with the rest of the digit. So 14 minus 14. If you get 0 or 7, then it is divisible. The initial number itself is divisible by 7. So here in this case we are getting 0. So 147 is divisible by 7. I'll give you another example. 154. So take the last number 4, multiply it with 2, 8, and subtract it with the initial number. So 15 minus 8 is 7. So it is 7. So hence it is divisible by 7. Suppose if this number is not 7, if it is also possible that it can be 14, 28, or some other bigger number. So when you get a bigger number, if it is two digit number, it is straightforward. If it is divisible by 7, sorry, I should say, or divisible by 7, then it is divisible by 7. If the two digit number is divisible by 7, then it is divisible by 7. Suppose if the number is so big that this number comes as greater than two digits, then what you do is you again repeat the same procedure. You again take the units digits, multiply it with 2, and then subtract it from the original number, like the leftover numbers. So you can just repeat this so many times until you arrive at a single or two digit number, and from there you can easily find if it is divisible by 7. So again, I'll give you the proof for this. As we already said, any number can be written as 10x plus y. Now divisible by 7. What I do is I subtract minus 21y. So 21y is divisible by 7, right? 21 is divisible by 7. So 21 into any natural number should be divisible by 7. So 21y is divisible by 7. And if you take any number divisible by 7 and another number divisible by 7, then this number also should be divisible by 7. So we are not changing anything from the remainder point of view. Now this is nothing but 10x minus 20y. So we can take 10 common out. We have x minus 2y. So if the original number 10x plus y, we had the number, we converted it into this form, then we added minus 21y. So everywhere, if divisibility 7 holds true, then even here the divisibility 7 should hold true. If the original number was divisible by 7, and even this should be divisible by 7. If you see 10 is not divisible by 7, so only this part should be divisible by 7. So x minus 2y. This is what the initial thing. We just took the units digit, multiplied it with 2, and then subtracted from the other digits, other leftover digits. So this is what we arrived at. So if this is divisible by 7, it is good enough to say the original number is also divisible by 7. Okay, this is the divisibility for 7. Now we go to 8. So in case of 8, so it is similar to the case of 2, 4. So 2, 4, only the units place. In 4 digits, last 2 digits. So in 8, if we can guess it, it should be the last 3 digits, right? So let's check if it is true. Again, any number, I am writing it in the form 1000, let's say a plus b. So again, 10 is not divisible by 8. 100 is not divisible by 8. Why? Because 8 into 10 gives 80. Again, plus 8 gives 88. Plus 8 gives 96. And the next is 104. So 100 never comes into the picture. So we go for 1000. 1000 is divisible by 8. Let's see. So 1 time we have 20. 2 times we have 16. 5 times we have 40. Oh yes, it is divisible by 8. How many times? 125 times. So this number is divisible by 8. So it never comes in the remainder. So it is only good enough to check just the last 3 digits. Here B represents the last 3 digits. That's why we have 1000 here. So 1, 2, 5, 7, 6. This can be written as 1000 into 12 plus 576. Correct? So this will be B. It is good enough to check whether this 3-digit number is divisible by 8. And then we can conclude whether this big number is divisible by 8. So we'll just check for this case. So 57. 7 times we have 56. 16. 2 times. Okay, this is divisible by 7. So this number is also 8. So this number is also divisible by 8. Okay, let's move to 9. For 9 also, the same condition holds true as 3. The sum of the digits, if the sum of the digits is divisible by 9, then the number itself is divisible by 9. Okay, so again, why this is true? Because any number we are writing it, we can write any, let's say a, b, c, d. This can be written as a plus 1000a plus 100b plus 10c plus d. Now 9, if you see, let's say c, 10 when divided by 9 gives a remainder of 1. So this we can convert as c. This is nothing but d itself. 100, again 9 into 11 gives 99. So 100 also leaves a remainder of 1. So this is b. 1000, 9 into 111 gives 999. So 1000 also leaves a remainder of 1. So this gets converted to a plus b plus c plus d. So this is also true for any higher powers of 10. When divided by 9, it leaves a remainder of 1. So it is good enough to check just the sum of the numbers if it is divisible by 9. For example, I'll give you an easy example. 9009. We know that this number is divisible by 9. So we'll just add and see. So adding, it gives 18. So again, if you add again these numbers also, if you add, it will give 9. So this is divisible by 9. So this first number we started with itself was divisible by 9. Next we go to 10. 10 is again pretty simple. So I'll say the multiples of 10. We have 10, 20, 30, 40 and so on. If you notice, the final digit is always 0. Right? So the divisibility rule for 10 is the last digit should be 0. So again, why is this the case? Any number, if you take 10x plus y, for y to be divisible by 10, it can only be 0, because y itself is only taking values from 0 to 9. This anyway is divisible by 10, so it never comes in the remainder part. Y, to get a remainder 0, it should itself be 0. So only the last digit is enough to check. Next we have 11. So 11, again I'll take a, b, c, d. We have 1000a plus 100b plus 10c plus d. D we write as it is. So divisibility by 11. So 10c. Now I need to introduce the concept of negative integers. Negative remainder. So that's why we require the knowledge of integers. So I'll take 2, or let's take 3. I can write this as either 2 into 1 plus 1, or I can equivalently write it as 2 into 2 minus 1. Right? So 2 into 2 is 4, minus 1 again gives 3. So now it is similar to writing it as 2 into 2 plus of minus 1. This is not going to change anything. So the remainder theorem holds true even if, for example, if you take 1, 2, 4, 8, 9, divisibility by 2. Even if we change one of them to negative remainder, for example 1, I can either write it as 1 or minus 1. So 2 will give 0, 4 will give 0, 8 will give 0, and 9 will, again I can write it as plus or minus 1. Doesn't matter. So at the end it is 0. So it is divisible by 2. I will give an example for not divisible by 2 also. 1 into 3 into 5. Divisible by 2. So 1 I can write as plus or minus 1. 3 I can write as plus or minus 1. 5 I can write as plus or minus 1. This again gives plus or minus 1. So the remainder is not 0. So this number is not divisible by 2. So in place of writing positive remainder, we can also use negative remainder. For example, 7, if the positive remainder is 1, then the negative remainder will be minus 6. For example, if you take 8, remainder of 8 when divided by 7, it gives plus 1. But also it is nothing but 14 minus 8 gives, 8 minus 14 gives minus 6. So minus 6 is also a remainder. This is only for convenience purposes because it is useful in certain cases such as these. We'll see why it is useful in the case of divisibility by 11. Also in some cases, okay, I'll just finish this and then explain it. 2 it will be minus 5. 3 is equivalent to saying it as minus 4. 4 is minus 3. 5 is minus 2. 6 is minus 1. So in some number when we are checking for divisibility by 7, suppose the remainder was 6. And if we choose to write it as minus 1, it is easier for us to multiply the remaining numbers, right? 6 into some number and minus 1 into some number, it is easier this way. So there also it is helpful. That is why this negative, representing this negative remainders are useful, and these comes handy in certain places. So this is one example for 7. Similarly for other numbers also you can write it similarly. This is nothing but this remainder minus this original number. Everywhere if you see this minus 7. Okay. So for 11 now we can see. 11, right? To prove this we just want, I'll take this. For 10, we can write it as minus 1. The remainder as minus 1. Right? So that is what we will be using. So for D it is D. For 10 we are going to write it as minus 1. So minus 1 into C is minus C. Okay. Then we have plus 100B. 100 is nothing but 9 into 11 plus 1. So the remainder is 1. So we write B as it is. Next we go to 1000. So 1000, how do we find the nearest 11? So let's see. So again 9. Let's divide by 11. So we use 9. 99. 10. So the remainder is 10 for 1000. Right? Because everywhere it is like 9 into 11 is 99. So 90 into 11 will be 990. So plus 10 will give us 1000. So 1000 has a remainder of 10. We can write it as minus 1. So it will be minus A. So it is similar for all odd powers of 10. Let's say this is odd powers of 10. The remainder is minus 1. And for all even powers of 10, the remainder is plus 1 when divided by 11. So if we have a number, we take all even digits. Let's say this is 0, 1, 2, 3. All even place digits. Or let's start from here. 1, 2, 3, 4. 0, 2, 3. Let's start this way. So all even place numbers. So D, B, add all of these numbers and subtract it with the sum of the odd place numbers. Okay. So this is the rule, and if this equivalent is divisible by 11, then the original number itself is divisible by 11. That is the rule for 11. If you want to take an example, I will take 594. Now we take these numbers 4 plus 5 minus 9. So this is nothing but 0. 0 is divisible by 11. Hence this 594 is also divisible by 11. Okay, next we can go to 12. 12 is again simple. 12 is nothing but 4 into 3. So if any number is divisible by 4 and 3, then it is divisible by 12. Okay, for example, let's take 132. So 1 plus 3 plus 2 is 6. It is divisible by 3. Again 32 is divisible by 4. So 132 is divisible by 4. So 132 is divisible by 12. Next is 13. Again for 13, the technique is similar to the 7 case, but here we take the number. Let's say the number is some xyz. We take the last digits, multiply it with 4 and add with the remaining digits. If this is divisible by 13, then the initial number is also divisible by 13. It is similar, the proof is similar to the 7 case. So any number we can write it as 10x plus y, right? So now what I am going to do, 39 is divisible by 13. So 39y is also divisible by 13. So I just add 39y. It should not disturb the remainder. So then I have 10x plus 40y divisible by 13. So again 10 I can take common out. I have x plus 4y divisible by 13. Now 10 is not divisible by 13. So only x plus 4y should be divisible by 13. So what did we assume? We assume initially the number is divisible by 13, and finally we arrived at if the initial number is divisible by 13, then x plus 4y should also be divisible by 13. So it is just enough to check if this x plus 4y is divisible by 13 to check if the entire number is divisible by 13. So let's see an example. I'll take 143. So I take the last digit, I multiply so I multiply this with 4, it gives 12. Now I add it to 14. 14 plus 12 is nothing but 26, which is nothing but 13 into 2. This is divisible by 13. So 143 is also divisible by 13. Okay. Next we go to 14. So 14 is nothing but 2 into 7. So if the number is divisible by 2 and divisible by 7, then it is divisible by 14. So we can extend this to any number of possibilities. It is same for 15. 15 is again 3 into 5. So the number should be divisible by 3 and it should be divisible by 5. Then it is divisible by 15. So in the similar way we can extend, we can also find for other numbers also. Given the smaller, given we know these many rules, it is mostly sufficient. And the other numbers we can, if you want to find a rule, it is most numbers are like multiple of something. So it is just enough to check if it is multiple of the smallest prime number, smaller prime numbers. That way we can also keep it simple. I hope you enjoy the session and are taking away some knowledge which you can utilize and better and ace your examinations. Keep learning. Thank you.